Today we are going to talk about regression analysis. Regression is prediction. Prediction is based on collecting data and use it to predict performance or outcome. In previous videos, we looked at the correlation between two or three variables, and a step further is to predict one variable from another. So the essence of regression analysis is that we fit a model to our data and use it to predict values of the dependent variable from one or more independent variables. For example, you would like to predict performance on a vocabulary test by knowing the person's motivation and the anxiety level. So you can use these independent variables, that is anxiety and motivation levels, to predict the outcome, the dependent variable. So in regression analysis is a way of predicting an outcome variable from one predictor variable. So here you do a simple regression analysis, or from several predictor variables, and then you do a multiple regression analysis. Outcome variable is the same as dependent variable, while predictor variable is the independent variables. So in regression analysis, you try to find a model to your data, the best fit. And this model is a straight line, is a linear line. For the sake of making accurate predictions, we want to fit a model that best describes the data. So you will see, if you have a data set, imagine a scatter plot, your data points are scattered all over the graph. You would like to find the line that best fits your data. And this straight line has two important characteristics. One is the slope of the line, which is the gradient, and the other is the point at which the line crosses the vertical axis of the graph, which is the intercept. The gradient and the intercept together are regression coefficients and are often indicated by small b. So if you see that in the literature, small b is regression coefficients. That will be important at the end of this video again. To exemplify or visualize the intercept and the gradient, you can see or you can look at these two graphs. In the first figure, there are two different lines with different gradients but the same intercept. The intercept is the point where they reach the y-axis. The second graph has three different lines with the same gradient but different intercepts. It's also important to note that the y-axis is always the outcome and the x-axis is always the predictor. So you would like to find the line of best fit, which will be the model. It results in the least amount of difference between the observed data points and the line. So you have observed data points that you collected in your research, and then you would like to find a line that best describes the observed data points. So here, for example, you have you measured anxiety level of people from 10 to 40, and then you also measured size of spiders, 5 centimeters, 10 centimeters, 15, 20, 25, and you wanted to predict anxiety level from the size of the spider. You can see that your data shows a positive relationship. So the correlation is positive. The bigger the spider, the higher the anxiety level. And this is the line of best fit. But still, since this is a straight line, it doesn't follow our data points. There are differences between the line and the data points. And these differences are called residuals. previously, we called them deviations. So these are actually deviations from the line. In order to express it in one number, you have to square these numbers because we have positive and negative values. Remember that if we add them up, it will result in a negative number. So the strategy we use is that we square them. So for example, if this one is -5, then you square them, it will be 25. So you square each value and then you add them up, and it will be the sum of squared differences, okay, or SS. If the square differences are large, the line is not representative of the data. So if it is large, it means that these differences are big. So this line is not very close to our data, so it doesn't represent our data. If the square differences are small, the line is representative. You find the best fit, but you would also like to assess how good your model is. And assessing means to compare it to a basic model. So it is important that we assess how well this line fits the actual data. And in order to explain this, I took an example from Andy Field's book Discovering Statistics Through SPSS. Imagine that I was interested in predicting record sales, so how many records are sold, from the amount of money spent on advertising the record. One day, my boss came into my office and said, "Andy, I know you wanted to be a rock star and you've ended up working as my statistics monkey, but how many records will we sell if we spend 100,000 pounds on advertising? If I didn't have an accurate model of the relationship between record sales and advertising, what would be my best guess?" Well, probably the best answer I could give would be the mean or average number of record sales, say 200,000, because on average, that's how many records we expect to sell. This response might well satisfy my brainless record company executive who didn't offer my band a record contract. However, what if he had asked, "How many records will we sell if we spend £1 on advertising?" Again, in the absence of any accurate information, my best guess would be to give the average number of sales, again the mean, 200,000. There is a problem. Whatever amount of money is spent on advertising, I always predict the same levels of sales. It's always 200,000, the mean. As such, the mean is a model of no relationship at all between the variables, okay? So it should be clear. And then that the mean is a very useless model of relationship between two variables, but it is the simplest model available. So if you would like to assess how good your model fits your data, then you can compare it to the mean as the simplest model. So you would like to see whether your model predicts your outcome better than the mean. And there are several indicators or values that can help you calculate it. Of course, SPSS does it for you, but you have to understand the mechanisms. So here in this figure, you see the mean as the model. Here are your data points, and these are the differences of your data points from the mean. Okay, so the total sum of squares uses the differences between the observed data and the mean value of the y-axis. In the second figure, you see the sum of squared residuals, or SSR, sum of squared residuals. So this is your best fit line, and this is the observed data. You can see the differences are smaller, but they are still differences, so these are residuals or deviations. And the third figure is the difference between the total sum of squares and the sum of squared residuals. Okay, so this is the model sum of squares. Okay, so you are familiar now with the total sum of squares. Differences if we use the mean as a model, sum of squared residuals differences if we use the line of best fit, and the model sum of squares, which is the difference between these two. Based on these values, you can calculate the R square. So this is the amount of variance explained in the outcome by the model. And you should multiply it by 100. So this is how you do it. So you divide the model sum of squares by the total sum of squares, and then you get a number, let's say 0.35, and then you have to multiply this 0.35 by 100, so you will have 35 as a result. So this means that 35 of the variance is explained by the model. For example, if you use the size of spider, so the anxiety level of participants is explained 35% by the size of a spider. Okay, so this is R squared. The other important indicator of value is F ratio. F ratio, this is the measure of how much the model has improved the prediction of the outcome compared to the level of inaccuracy of the model. So here, again, you have an equation. So the F ratio is the division of these two indicators. We are not going to go into this. So if the model is good, your model that you chose, then we expect the improvement in prediction due to the model to be large. So this MSM will be large, and the difference between the model and the observed data to be small. So, in short, a good model should have a large F ratio, which is greater than 1 at least. Okay? So we would like our model to improve the prediction, and we would like those differences, remember, between the observed data and the line to be small. Then the second table that is generated by SPSS shows the individual predictors. So a bad model, for example, the mean, will have a regression coefficient, remember the gradient and the intercept, of 0 for the predictors. That means if the regression coefficient is 0, then a unit change in the predictor variable results in no change in the predicted value of the outcome. That means if you increase the money you invest in advertising, there will be no change in sales. So you will not sell more records, even if you advertise more. And the gradient of the regression line is 0, meaning that the regression line is flat. And it should be different from 0, but also significantly different. So there will be a t-statistics that should be significant. We'll talk about it soon. And then let's look at an example. Please open the data from either from below this video or from the Google Classroom. So record 1. It takes some time. And here you can see two variables which are labeled nicely in the variable view. So we've got the advertising budget, which is expressed in thousands of pounds, and we have the record sales, which is again expressed in thousands. Both of them are interval variable. First, we would like to see how these two variables are related to each other. So we create a scatter plot, and we would like to see how the advertising budget is related to the record sales. And yeah, it's very small here. And here you are. We fit a line here. Yes, linear. And you can see that there is a positive relationship between advertising budget and record sales. And there are some sales here in the top left corner, which there are some records which are sold even if you don't invest like budget any money. Okay, so there is a positive relationship. Let's see whether advertising predicts the sales or explains at all. So for that you go to regression, linear, and again your independent variable is advertising and your dependent variable is record sales. You click on OK, small again. So the first table generated by SPSS is the summary of the model. So first you have a simple R, which is a simple correlation between the advertising budget and the record sales. So there is a positive relationship. We could see that in the scatter plot as well. Here the second number is the R squared, which is 0.335. This has to be multiplied by 100, remember from the slides, and it will be 33.5%. And this can be interpreted that 33.5% of the record sales can be explained by advertising. But still, there are around 60% of the sales that cannot be accounted for by advertising. So there are other variables that contribute to the record sales. The second table is the ANOVA. Here you can see all the numbers that we just discussed. This is the model sum of squares. This is the sum of squared residuals, and this is the total sum of squares. And here you can see the MMS, the MSM and the MSR. And the division of these two gives you the important value, which is the F value. Here the F is 99.59, which is significant at P is smaller than 0.001. So this means that our regression model results in significantly better prediction of record sales than if we use the mean value of the record sales. So our model is better than the mean model. So overall, the regression model predicts value of record sales significantly well. And the last table is also very important, which is the model parameters. So you would like to see the individual contributions of the variables in the model. Remember the regression coefficients. We had the intercept and the gradient. So the constant B in this table is the intercept, which is 134.14. So this means when no money is spent on advertising, so you spend no budget on advertising, then still 134.14 records will be sold. Okay, and this is the gradient, which shows the change in the outcome if you change a unit in the predictor. So if you increase the unit of budget by 1, then the sales will be increased by 0.096. But remember that our data was in thousands of pounds, so you have to multiply this number by 1,000, and then it means that if you increase your budget or advertising by 1,000 pounds, then it will result in 96 extra sales. And this is what regression actually tells you, that the variance that it explains by the variable, how good your model is, and then how many increase can you expect in your outcome. Okay, thank you.